Hello friends, welcome to the stereochemistry lecture again. The topic of today's discussion is erythro and threo nomenclature. This nomenclature is based on 4-carbon aldose sugars, d-erythros and d-threos. If you look at the Fischer projection formula of d-erythros and d-threos, the two chiral centers are different and the two different substituents CHO and CH2OH are on the vertical lines. In erythros, the two hydroxyl groups are on the same side and the two hydrogen atoms are on the same side too. In threos, the two hydroxyl groups are on opposite sides as are the H atoms. If you have a system like RXYC, CXZR prime, you can apply this nomenclature. For drawing Erythro Diastereomer, draw an skeleton for the Fischer projection. Put groups R and R prime on the vertical lines. Same groups X on one side and Y and Z on the other side, where Y and Z may be same or different. For drawing Threo diastereomer, draw an skeleton for Fischer projection. Put R and R prime on the vertical lines. Two same groups X on opposite sides and Y and Z on opposite sides too. From these structures, we can see that erythro and threo are not mirror images and thus these are two diastereomers. Now we are going to take the example of 3-bromo-2-propanol. There are two chiral centers, so there will be 4 stereoisomers, 2 erythro and 2 threo diastereomers. Each diastereomer will have 2 enantiomers. For drawing an erythro diastereomer, draw an skeleton for the Fischer projection and you can put either same or different groups on the vertical line. Let's put CH3 on the vertical lines. Now put both the H on the left and OH and Br on the right. The second erythro isomer will be its enantiomer like this. For drawing one of the two threo isomers, draw an skeleton for the Fischer projection. Put methyl groups on the vertical lines. One H on the left and other on the right. Now put OH on the right and Br on the left. The second threo isomer will be its enantiomer like this. Let's take the example of ephedrine. For drawing an erythro diastereomer, draw an skeleton for the Fischer projection and put methyl and phenyl on the vertical lines. Put both the hydrogen atoms on the left and OH and NHMe on the right. The second erythro isomer will be its enantiomer like this. For drawing one of the two Threo isomers, draw an skeleton for the Fischer projection, put methyl and phenyl group on the vertical lines, one H on the left and other on the right. Now put OH on the right and NHMe on the left. The second Threo isomer will be its enantiomer like this. Now let's have two examples A and B to find whether they are erythro or Threo. Till now, whatever we have learned about erythro and Threo isomers, molecules were represented by Fischer projection. We know that in a Fischer projection formula, molecules are in eclipse conformation. The given molecules are in staggered conformation. So, in staggered conformation, the definition will be reverted. Means, in erythro, same lateral atoms or groups on the two chiral centers will be on opposite sides, while in Threo, same lateral atoms or groups will be on the same side. Let's first put missing hydrogens in A and B. In structure A, two hydrogen atoms are on the same side, so it is Threo. In structure B, both the hydrogen atoms are in the opposite side, so it is erythro. Let's take the example of hydrogenation of a prochiral alkene generating saturated molecules with two chiral centers. Here, we have to find whether the products will be erythro or Threo. Palladium catalyzed hydrogenation is a syn addition, means the two hydrogen atoms add to the same face of the double bond. In the given alkene, there are two faces of double bond with equal probability for the addition of hydrogen. Hydrogenation from above the plane of the molecule will give structure A, while addition from below the plane of the alkene will give structure B. Both A and B are in eclipsed conformation, and in both A and B, the two deuterium atoms are on the same lateral side. So, these are erythro isomers. If we rotate structure B through 180 degrees in the plane, we can see that A and B are enantiomers. So, we can say that these are erythro enantiomers. Let's take the example of bromination of the same alkene. Bromination of an alkene is an example of anti-addition, means the bromine atoms will attack from the two opposite faces of the alkene. If attack occurs like this, it will give product A. If attack occurs like this, it will give product B. A and B are in staggered conformation with the same lateral deuterium atoms on the same side. So, these are Threo isomers. If we rotate structure B 180 degrees in the plane, we can see that A and B are enantiomers. So, we can say that A and B are Threo enantiomers.